Hi, I'm Tim, and I'm going to be talking about using Python for FPGA-based hardware. But before I get to that, I'm going to do a little advertisement. This thing is called the Tomu. It's basically a microcontroller that fits inside your USB port. It's all open. It costs about $10. I have them here. If you want one, you can send me a pull request. Doesn't matter what the pull request is. If I accept it, you get a device anywhere in the world, or you can give me $10. But I much prefer pull requests. Pull requests are the preferred way to get it, or you can go on Crowd Supply and buy one yourself. Bunny software guy, Zobs is the one running Crowd Supply's fund campaign, not me. So don't blame me. Yeah? Okay. I'm not used to handhelds. So, now back to our main topic. I love Python. I love Python so much that I started a conference dedicated to it in Australia. But I'm also a practical person, and I strongly believe that you should use the right tool for the right job, not use Python for everything. Python is a great language, and I love it, but it's not the right tool for everything. And so if you'd talked to me probably 5 years ago and said, I'm going to use Python for FPGA-based stuff, I would have said, you're crazy and you should not do that. Nobody does that. That's a silly thing. But today, I say yes. And I'm hoping that explain why I think yes and why you should be doing this as well. Who here has used an FPGA before? Okay, there's lots of people. I'm a software guy, and I'm not a hardware guy. I dabble in hardware and pretend to understand hardware, but I don't. And the story of this HDMI to USB TV project is the story of me trying to apply software to hardware. And so, about in 2012, I decided I wanted to make it possible for people who are remote to attend conferences easily. So I started this project called Tim Videos. I'm not very imaginative for naming things. And started to figure out how you record and live stream a conference. And this is kind of the setup that you build to record and live stream a conference. The problem we had is that the world had moved towards HDMI in the time that it took me to figure out how to do this. And HDMI, we want to capture a really good high quality stream of the HDMI because pointing a camera at the screen gives you really terrible things. The contrast is really horrible, these type of things. So I ended up having to develop this custom open source hardware called the HDMI to USB. And they sit basically in this position between the presenter's laptop and the projector and give you a high quality capture of whatever's going to the screen. And as far as the presenter is concerned, they're talking to the projector. There's no understanding that there is something there. So it's kind of a man-in-the-middle attack for video. So I had to create this hardware for HDMI, DVI capture, and the reason I needed to create it is because I wanted to solve the problem of the presenter plugging in their laptop and not getting something up on the screen at like forever, you know, like it keeps, like every time there's a new standard, it seems to get worse, and then things get a little bit better, and then it gets worse, and we've all experienced it. And so I created this device to do the effective man in the middle. When you connect it to a computer to do capture, it just appears as a webcam, so you can use it with any device, like Chrome if you want to go to YouTube, or like any other capture. The other interesting thing, though, is it appears as a serial port. And you can connect to the serial port and get debugging information about what's going on inside the HDMI core. And this is why I had to do this, because when somebody plugs in, I want to know why they're not getting a signal on the video. Not that they're not, I want to know why. Are they projecting the wrong resolution? Are they projecting, not at all? Is the cable not plugged in? These type of things, it's really useful to have a serial port that says, I just saw somebody plug in on this port, or they're sending 1080p, but you told them to send 720p. And as I said, I'm a software guy, and so FPGA have these nice properties of making hardware problems into software problems. I can update it after the fact. If I make a mistake, I can fix it. I'm a terrible programmer, like every human on the planet, and I write lots of bugs. And so I don't want my bugs permanently coded into a piece of silicon, and I probably couldn't afford to do it anyway, so that's why I ended up using these FPGAs. The problem is that the two major languages are Verilog and VHDL for programming an FPGA, and neither of these are Python. But as I said, I'm practical. Everybody uses VHDL or Verilog, depending on where in the world you are. If you're here in America, you tend to use Verilog. If you're over in Europe, you use VHDL. I don't like either of them, but I don't like a lot of things, and I still use them. So I was like, okay, everybody else has blazed the trail here. They have decided that VHDL and Verilog is the way to go. And so that's the way I followed. We built the firmware for this FPGA to do the capturing based on basically a mixture of VHDL and Verilog, and we kind of almost got it working. It took us about 3 years. We only had basic features. We could do matrix switching. We could do USB capture, kinda. But the other thing that really frustrated me as an open source person is that the license of the code we're using was kind of questionable because it had come from things like the application notes that people had written and the core generators that the tools had. And the dev board we were using wasn't open source, and I'm an open source person, and it's a dev board. It's not designed to be used at conferences, so we designed our own board kind of based on that design, but with things like putting all the ports on the same side rather than you got to be piggery around it, making it so it could fit in a rack mount case, things like that. And so now we had two pieces of hardware. This one has a bunch of features that aren't on the other board. That is 90% the same, but there are some differences. And we needed to refactor the code to try and deal with these differences. And we just really, really struggled to make this work. Every time we made a commit that would fix something on one board, it would break something on the other board, and all these type of problems. And I'm a software engineer. I do web stuff and support 5, 6 different browsers that are totally incompatible in the way they render centering things on the table. Why can't I make something as simple as this, which the 90% similar work? And that was really frustrating. And so after about 4 or 5 years, I'd gotten to this point where I was very frustrated. This project wasn't really making sense, and I was looking for alternate solutions. And I came across this thing called Migen, and the interesting thing about it was Python based, and I knew I liked Python. It also had a bunch of these other things that we needed, like a HDMI capture core and a DDR RAM and Ethernet, and already supported about 20 boards. So I thought, why not try Python? I mean, the worst comes to worst is I waste a bunch of time, but I'm not having fun what I'm doing now anyway, so a distraction might be good. I'm going to come back to it with a fresh set of eyes. So what I ended up doing, though, is instead paying somebody else to do it for me. So this company called Enjoy Digital, I asked them to basically recreate the functionality I had in the Verilog VHDL design in this Migen Litex technology. And he came back with a quote, and I said, that quote seems way too small. We've spent like 4 years working on this. Why can you do this? And he said, nah, I can do it. And I thought, oh, well, what's the worst case to worst? I give them money and then get nothing. But in 4 weeks, he had lots more features and a working solution compared to our attempt of doing this for like 3 to 4 years. And it supported both boards very easily. It supported Ethernet. That was on our radar. We wanted to support Ethernet for a long time and just never had been able to make it work. Not because Ethernet itself is hard. It was like as soon as we added Ethernet, all of a sudden it didn't fit on the design, the FPGA we were using. And it was like compiling in like a 1/10 of the time our previous design was compiling. It seemed really awesome. And so we kind of had this situation where I had this original firmware that was written in VHDL and Verilog. It was hard to extend, it was questionably licensed, and we totally replaced it with this Litex firmware, which was Python-based, supported multiple boards. We now support, I think, about 12 boards, and a bunch of different FPGA technologies. It had Ethernet, it had triple buffering of the video in DDR-RAM, and to make it even better, all the code was released under BST MIT license, and there was no vendor code in it whatsoever. So it was a truly open source thing. And now we're using it to record conferences all around the world. It's recorded PyCons, it's recorded linux.conf.au's. I'm an Australian, so you know it's been heavily used in the Australian open source industry, but it's also used at places like DebConf around the world. They're obviously very invested in the open source nature of it and are now using it to record their conferences. And so, I guess, yay Python. But I've just described magic to you. If you magically do this thing in Python, you magically get better results. If I was to stop the talk here, you'd probably go away and think, oh yeah, what's this guy? He's a bit crazy. So let's dive deeper into why I believe this system is so much more effective than our old system. And maybe you don't want to buy into the Python idea, but if you're an FPGA programmer, the high-level concepts that I'm going to describe here, I'm very sure that if you follow these, you'll be a more effective FPGA programmer, even if you're doing VHDL and Verilog. And I wish that if I was to go back and forced to do a VHDL and Verilog project, I would do it the way I do the Python project now. But it took switching to Python and really understanding the power of doing it this way that helped me understand how to be a more effective FPGA programmer. And in the kind of 2 years since we've switched to Python, things have gotten a lot better, a lot quicker. And we have now a huge array of features that I didn't think we would even ever get. I'm going to take a quick drink. So these are, I believe, the 4 reasons why doing this project was hard. So the first thing, oops, I've gone one too far, is that existing HDL languages suck because the HDL languages, they're not a programming language, and what you're really doing is programming. They're designed to describe hardware logic, but ultimately most of what you're doing isn't describing hardware logic. It's describing how things are connected together and, you know, how this board is laid out and these type of things. And that very much is what a programming language does. And so this was one of the key things, is that VHDL and Verilog aren't programming languages, they're not Python, but Migen is. The thing about Migen, though, is it doesn't take Python and directly convert it to hardware. That would be a pretty hard task to do. What it allows you to do is describe hardware and how hardware gets connected in a much more, what I feel as a software person, natural way. It's effectively a HDL, a hardware description language, written in Python that generates Verilog. And it allows you to think of things at a much higher level and let the Python code worry about the details like clock domain crossing. If it's trying to connect two things together that are different clock domains, why do I have to worry about how that happens? Somebody who's much smarter than me should solve that problem once, and maybe there's a couple of options and I have to figure out which one's the best one in this, whether it's a FIFO or a double register or any of these type of things. But I shouldn't have to figure that out myself as a hardware engineer, just like I don't have to figure out which registers are allocated for in my compiler. The compiler does it for me. And if I really want the very expert performance, then maybe I do care about register allocation. But most of the time I don't. And so you can think of Migen as an easy way of generating Verilog. And that's kind of what I do. So let's start with a simple example. This is a blinking LED. This is kind of what Migen looks like. And this here basically creates a counter that increments every cycle, and then this connects the top bits to the LED. And so this is kind of a way to blink an LED. And I believe because Python is a programming language, we can do a lot more interesting things. Like this fact that signal is sized automatically for whatever I pass in as the max cycles. If I want to do multiple LEDs, I use a for loop. And this will generate multiple combinational signals which connect multiple LEDs to the same set of output. And so if, for example, you had a CSV file which lists all the LEDs and which pins they're connected to, you could use a for LED in CSV file open to generate your Verilog. And Python is really good at that. String manipulation, kind of connecting data sources together is something that Python is very good at. The other great thing is that Python can generate exactly what is needed for that Verilog. If you're generating for a Series 7 device versus a Spartan 6 device, you actually want slightly different Verilog output because ISE is a lot more stupid than Vivado. And so frequently you want to tweak your output based on your target. And Python can do that. Python's very good at tweaking output. So you should use a programming language, not a HDL language, when you're doing FPGA design. And so I think that's pretty awesome. But I only really circled the top one there. There's still 3 other things here, right? Writing hardware is hard, and writing hardware is a slow process. So my solution to that is reduce the hardware you write. It turns out there's these great things called CPUs, and CPUs are really good at doing most things, which is why, like, we use them pretty much everywhere. And there's, you know, a $1 trillion industry based around things that run on CPUs called the software industry. And the great thing about an FPGA is it can pretend to be a CPU. You can put a soft CPU in your design. And that was another thing that we realized, was that if we have a soft CPU, we're doing less in the FPGA. A lot of what we wanted to do is provide a command line, human accessible serial interface. This is really hard to write in VHDL, but as a trivial C program, like the first program you write in C is like hello world. The second program is probably something to take some input and change an option or something. And C code compiles really, really fast when it's trivial. Like GCC can compile a couple of 100,000 lines of C in like seconds. And it's very easy to update as well. If you have a CPU, you can load new software on it very, very easily using things like Ethernet and serial port and all that type of thing. So that's kind of what Litex and MeSoc build on top of Migen, is this kind of system on chip, which is a library of cores with a soft CPU that allows, and like a CSR bus is kind of what is added. And the interesting thing is that unlike vendor tools which make you use the soft CPU core that they designed, which prevents you from switching to another vendor's FPGA, we actually are very agnostic about which soft CPU. We support 3. I'm sure if people wanted to add more, they could. We also integrate fairly heavily with the peripherals in providing a common interface for config status registers that we generate C stubs for. So all your C code doesn't say write to memory JES 200 for the UART. It says UART write status. And it doesn't matter where in your memory map that ends up with. You just call it and the automatic generated C writes it to the right location. And so back to our simple example, we could use an LED blinks quite slowly. We could use a GPIO CSR register. And so this is what the code looks like. You effectively say, please give me a GPIO CSR register and connect it to the LED. It's like one line. And then I write a little bit of C code that, as you can see, this is an IO module, LEDs, write 0, and that will turn on the LED. So this is pretty simple. As a real-world example, when you bring up SRAM, you generally have to do training of the SRAM. In our system, we use the soft CPU and some C code to do this training. Turns out that our soft CPU implementation, the LM32, uses about the same amount of resources as the HDL for doing training does in the Xilinx MCB. So the other great thing is that even if we only used it for training, at the end we get a soft CPU for free. And this is really cool. There are some downsides. Now you need to worry about having GCC and BINU tools for the soft CPU architecture available. To solve that problem, we've basically provided pre-compiled packaging system for all that as part of a build environment that makes it very quick and easy to build your FPGAs. Firmware. The other thing is there's a smaller community. Like if you go and search for Spartan 6 Verilog on Stack Overflow, you're likely to get a hit. And then like 10 people telling you you're doing it wrong and offering a wrong suggestion, and then another 10 people correcting those 10 people. And yeah, I would not trust any Verilog solutions I find on Stack Overflow. The problem is that this is C and it's not Python. So I'm a little bit crazy, and there's this great thing called MicroPython. MicroPython is a Python designed for little CPUs. So I have this project called FUPI, which is FPGA MicroPython. It's still a work in progress. We have the UART working, and you can write to the random memory addresses, but it's still in progress. But I think the key thing here is push as much as you can out of the FPGA stuff. Only the stuff that really needs the high speed, like the video stuff in our case, needs to be in the FPGA. All the interacting with the users are like, slow. They take seconds to decide things. So we can have a soft CPU running at like 50 megahertz, and it's like bazillion times faster than them. So reduce the hardware, you're right. So that's another big thing that I learnt from this approach. And I found that Litex and Migen are a really good way to have a soft CPU in your system that doesn't tie you to a vendor. But I still haven't covered everything on this list. Writing hardware still is hard. It's got hard in the name, right? So it's also kind of slow. And the reason I feel is that you load your design into your FPGA and then it doesn't work. And then you sit there and go, well, now what? And I think one of the other things we've done is increase the ability to inspect what's going on inside your FPGA. And this becomes easy once you have a CPU, because this is kind of what you get inside a Litex environment. You have some peripherals, you have some DDR and some memory, and there's a bus, and then there's a CPU. But it turns out when you're developing stuff, you have a very powerful CPU kind of sitting on your desk. It's called a computer. And so why don't we just make that the CPU? I can like connect GDB to a program running on my computer. I can like single step it. I can printf things. That's really powerful. And so Enjoy Digital has built a bunch of bridges. And the interesting thing is that it's kind of agnostic to the interface that it runs over. We have a bridge that runs over UART. We have a bridge that runs over Gigabit Ethernet. We have a bridge that runs over PCIe. The interface is still the same, and it's Python. So who here has used the interactive console like TypePython or IPython or something like that? Well, that's what you do. You import the bridge, and then you say, well, open the remote client, and it goes and opens the FPGA, and then I can write directly into the memory location there with that value, or I can read it and it gives me back values. This is super powerful in allowing you to quickly change a bunch of settings and see whether those settings work instead. The great thing about Python, though, is everything in Python is kind of inspectable, and there are things like docstrings, and so you get things like a mems object that describes your memory map, so you know where to write things to. All the registers have names like IO module LEDs, the same as the ones that we were looking in the C function. And I can just say, write to my IO module LED 1. I don't have to worry about where in the memory location it is. I have a terrible memory. I can't remember whether I put it at 2000 or 2002. Why should I actually care? And then you combine it with something like IPython, and you even get tab complete on your register names. That's pretty cool. So you should increase the inspectability inside your FPGA. And so that's really cool as well. But there's still one that I have not talked about, and that's this bottom one. FPGA toolchains are slow. And some of it is the fault of the vendors not caring, but FPGAs toolchains do have to solve hard problems. It is actually a hard problem to map arbitrary logic onto a real-world design. It's like trying to solve hundreds of traveling salesman problems all at once. And the more stuff you have, the harder and harder it becomes. especially if you're not buying really huge FPGAs. I'm a hobbyist, I do this as a hobby. So I want to put it on as cheap a FPGA as possible. And I'd much rather dedicate the money to, paying for coffee for people than dedicating it to FPGA resources. So we need to reduce the hardware on the FPGA. Especially when developing, where we're trying to iterate quickly, right? You want to try something, see whether it works. And when you're developing, you kind of look at this structure, and the thing you're probably working on is a peripheral, right? Like this thing here. You're just working on one of those at a time. Like, unless you're Florent, you're probably not working on the DDR memory controller and adding new support. You're probably not working on a flash or something like that. You're only working on a peripheral one at a time. So why do we need the rest of this stuff? Why couldn't we just have just the peripheral and maybe a little bit of glue logic? And it turns out we can. The bridge just bridged directly onto the bus. So we can just have only the peripheral. And it turns out when you remove 90% of the stuff that goes on the FPGA, you get a very, very small design. All we have is a simple little bridge which takes some arbitrary data and converts it into a couple of transactions, and your peripheral. And this is really small. And when it's small and you put it on a larger FPGA, your compile times are fast. And so when iterating with a design like this, you can get iteration times of minutes rather than the average time we get with a full thing is like 5 to 10 minutes, and with everything, about 30 minutes. I mean, even that is pretty quick, as far as I know from friends who have larger designs. But with this thing, it's very easy for the FPGA toolchain to solve this problem. So reduce the hardware you write on the FPGA. So I think that's really cool as well. So I kind of, in summary, these are the main reasons I think developing for an FPGA is a lot more painful than it should be. And I think we have kind of a little bit of proof that our way allows us to be more effective. And maybe it's because we're all crazy and software developers rather than hardware developers, but we really believe that using a real programming language, reducing the amount of FPGA hardware that we write, increasing the ability to see what's going on inside your board, and working on small bits independently at a time that are reusable, has made us significantly more effective. And I think the results really show how much more we can get done now with this type of design. And I think Migen, Litex, and Mesoc give you a lot of these features. I won't say they're perfect. There are a lot of issues. But Python really is a powerful, productive language and allows us to do a lot of interesting things we wouldn't otherwise be able to do. Having a soft CPU, if you're not putting a soft CPU in your FPGA design, you're crazy. Like, as I said, if you have DDR memory, the soft CPU is about the same amount of resources as if you did the training in HDL. So move the training to C code, which is a bunch more understandable, and then get a free soft CPU that you can use for other things. And bridges, I think, are also really interesting way to help accelerate your design. So our goal is to make presenting, recording, and live streaming easy, and we're getting there. We're not perfect. We need your help. There is so much more we could do. The great thing about it is this is all open source, so if you want to reuse our stuff in some other way, I keep getting people who want to use it for upscaling retro games in real time. You could do that. Visual DJs are very interested in having hardware that they can do effects on at the pixel level and things like that. And so we need your help. The hardware we work on is a little bit more expensive than the Tomu, but if you contribute, you might find it turning up on your doorstep. I've done that for quite a few people who have contributed and have been money poor but time rich, especially students. If you're a student, I highly recommend contributing because I think students are awesome. Even if you don't know anything yet, I didn't know anything when I started this. So like, you can come a long way in just a couple of years. And this is kind of what goes wrong when you screw up. Whoops. Yes. That's a lot more effective at freaking out the AV team when you put it up full screen. So yeah, that is my talk on how the HDMI to USB project worked. I was going to give a demo, but it appears their recording system does not like 720p60, only likes interlace, and I don't do interlace. Interlace is an abomination. I also, somewhere around here, have one of the boards that I designed, the FPGA board. You can come and have a look at it. This one's Carl's. He stole some of mine, so I'm less concerned if you destroy this one, because he owns that one. But it'd be nice if you didn't destroy it, so be careful. Do we have time for questions? Cool. Guy up the back. So the HDMI, the question was, a lot of the things I described should have been in a CPU anyway. What actually about your project needed the FPGA speed, and why do you think Python was suitable for that? So I gave a talk on this at the 33C3, so not the last one, the one before it, called Dissecting HDMI. And this talk went into detail about how our HDMI receiving core works. And that really does need the speed of the FPGA because there's no CPU out there that really is able to bit bang HDMI, but these FPGAs effectively can. And so we run HDMI directly into the pins of the FPGA, which allows us to write the HDMI core in the FPGA. And this is what gives us our debuggability, our ability to do things like we know if there's some type of cable that's dodgy where one of the channels is broken, because we can see individual symbol error rates for each of the channels. We can see what speed the pixel clock is. We can get all these really cool debugging information, and I think there's a break between the two talks? No? Yes? If you come up afterwards, I can actually show you some of the serial console. I've got one of the devices working down here, and I can show you some of the interesting debug information we get.
No, that's outstanding. And there are a lot of things in here which I thought were really ideas.
Yep.
What I'm saying here is, when I'm writing an FPGA in one of those horrible languages, or both of those horrible languages, there's a lot of work that goes time to say, oh, we ought to be able to write that in C instead of system C and stuff like that. And
You're talking more high-level synthesis languages.
I'm trying to picture what you're doing in that context, actual.
I don't know a huge amount about high-level synthesis, which is the idea of taking, say, C code and compiling it directly onto an FPGA. My understanding is that gets pretty poor results, at least historically. The amount of FPGA resources you need tends to outweigh the advantage you get. I would not recommend Python for a HLS type workflow for the simple reason that Python is a very, very high level language where you can do anything. Although the PyPy guys might disagree with me because they've done some crazy stuff like implementing Python in Python with a JIT that is able to beat C code for doing things like matrix multiplications and stuff like that. They're crazy. Even I think they're crazy, but yes, they actually have performance numbers that prove that even if they are crazy, they can do it very quickly. If you're interested in that type of area, the PyPy guys might be able to tell you how maybe you could do the same thing translating it to an FPGA. But yeah, that's way out of my brain capacity. Yep.
I was just wondering if you played around with any of the hybrid hardware, like Zincs, and if you have, how you would characterize, the real CPU versus the software.
So at the moment, we don't have support for Zincs in LiteX/Migen. There are about 3 different projects in progress at the moment to add support for Zinc in different ways. Some people just want the Zinc to be a Linux computer. Some people want it to be running bare metal code and running generated C code. And these type of complexities make the problem quite a bit harder because the type of C you want to generate is very different if you have to go through a device driver than if you have to do bare metal across the bus. And generally, like, in all our situations, it's been better to pair a Raspberry Pi with a FPGA than it has been to have the ARM embedded in the FPGA. If you look at how fast the Raspberry Pi 1 is compared to the Raspberry Pi 3 is, and look at the speed of the Zinc processor internally in the FPGA has changed in the same period, I feel like the Raspberry Pi has gotten a lot more features in a lot shorter time, whereas like the FPGA side of things in that same time hasn't really changed. The Zincs, like, if you go to the high end, where you're paying, thousands of dollars per chip, then yes, things have gotten a lot faster. But at my end, where I'm paying, maybe $30 a chip, the Zinc ARM processors haven't really gotten faster quickly at all. And the FPGA matrix hasn't changed at all in that period really either. Yeah, I think pairing it with a Raspberry Pi is $35. Hard to see how much functionality you get in a Zinc for $35. If you're in robotics, a Zinc might be actually quite good, but I don't do any robotics stuff. I am mainly in like capture hardware and yeah, and like in this case, they're pretty much always connected to a computer anyway because the computer does a whole bunch of video encoding and sends it to the internet or does live mixing if you have like 6 or 7 different feeds and these type of things. I think as I described all the way back at the beginning.
Well, you're right, it's to USB, so it's going to a computer.
Yeah, I mean, it actually has gigabit Ethernet, and very soon we will not need the computer. We will just stream directly over the Ethernet. But because USB works well enough for us, that hasn't been a top priority. The problem is, when things work, the pressure to get the next thing to work is less, there. Yep.
So a question about the
They're written in Migen, so they're actually written in Python, this HDL language that allows you to effectively generate the Verilog. And so all the HDMI core, all the memory core, that's all pure Migen. There's no Verilog in there. The soft CPUs are they're written in Verilog and just wrapped. So we haven't re-implemented the whole CPU, soft CPU. But some crazy people are doing RISC-V based CPUs in Migen directly, and that's allowed them to do some very interesting things like taking the spec directly, passing it with Python, and then generating the code directly from the spec. I don't necessarily think that's a good idea, but when you're in a programming language, it's something you can attempt to do. But you know, like the Jurassic Park thing, just because you can doesn't mean you should. But yeah, at least people can attempt, and we can find out whether this was a good idea. Probably wasn't, but can you predict that, you know, hailing a random stranger to turn up and drive you places was going to be $1 billion idea? I wouldn't have. So, you know, I'm all for enabling people to do experiments that I think are crazy, because occasionally one of them is a good experiment. One more question. He was quicker, I'm afraid.
Are there good learning resources out there for Migen? Or is it kind of a learn HDL, Verilog, well, and then like get used to Migen?
It depends on what you want to do. That is one big downside of Migen, is that there's just not as many resources, and it's something I've been concentrating on trying to improve. The accessibility to get into Migen and LiteX stuff by improving the documentation and the environment setup. The one thing I dislike about Python is packaging. It's a huge mess. And so we've built in what I call the LiteX build environment, which allows you to effectively run one command and get the complete LiteX setup. You then have to go and get the vendor tools, because their licenses prevent me from, you know, scripting, downloading, installing that. But other than that, it gets the full, like, Python, it gets your full compilers, it gets your full board definitions, all this in one. That if you're crazy, you can curl and run it straight away without, you know, even knowing what it does. But please download it and have a look what it does and then run it. It doesn't need root though, so if you're really paranoid, you can run it as another user that doesn't have permission to hose your machine and stuff. In fact, it'll complain if you try and run it as root. It'll say no. So I think that's it. If you're interested in coming and having a look at the hardware, or, you know, getting a Tomu, or you've got some idea that you think the Tomu would be useful or interesting for, I'm happy to talk about that to people as well. Cool, thank you very much.
Thank you.